Hello, everyone. So welcome to our second video about optimization problems. We're going to do a few more challenging problems. So now that we're getting to be experts after the first video in optimization problems. So optimization problems continued. Oops, could be if I spell it right. Okay, so number three, third example in the optimization series. So here's what we want to do. In this case, we want to build another fence like in the last video, but now we have to worry about costs because we have a certain budget, which is something reasonable. So now this is a situation where we want to like fence in a nice yard, but we want to stay within budget. So how is the optimal way we can do this? That's what the question is going to be about. So you want to build a rectangular fence area with three sides made of chain link fence and one side made of wood. The chain link costs $10 per foot, and the wood fencing costs $20 per foot. So the wood is twice the price. Oops, sorry. What is the max area we can enclose if we have a budget of $600? Okay, so again, we're going to follow our 4 or 5 step program, depending on what we want to need to solve for at the end. I think this we can do it in 4 steps. Maybe we need, but anyhow, we need to begin by drawing a diagram. And introduce variables, as always. Okay, so I'm going to say let X and Y be the sides of the rectangle. We'll draw a little rectangle. So we have X. I can call this Y and call this X. But now there's added information, right, that we didn't have before. 3 sides are chain link, right? And 1 is wood. So I'm going to let these 3 sides, and it doesn't matter which 3, be the chain link. And notice the chain link is, chain link looks like this. Metallic loops, right? So those are going to be the gray. The gray is going to be the chain link. So we have to kind of impose this information, extra information on the diagram. That's not part of the geometry, but it's going to be part of the constraint information. So the constraint information is not geometric here. So that's why this is a little more tricky. In the last example with the house fence that we did at the end of the last video, the constraint was just on the amount of fencing. It was a geometric constraint. This is on the cost of fencing, so it's out with the geometry. So we have to add this information to the diagram. And this will be the wood, okay? There we go. So just so you can visualize what's going on. Okay, and so brown is the wood. Now, you don't technically have to draw this in the picture, but I think it helps you keep track of the information and visualize it in an easy way. You could just do it by going back to the statement of the problem, but it's easy to miss it that way. So I'm going to put it in the picture. Okay, now again, step 2, we want to maximize area. So the area, again, for handy dandy rectangle is x times y. So that's easy. Step 3, now the constraint. And use it to rewrite, find the constraint equation and use it to rewrite the area function as a function of one variable. Okay, so now this is trickier because the constraint has to do with the cost, right? So let's go back up to the statement of the problem. We have to kind of underline the information that's involved in constructing the constraint. So we have a budget of $600. The chain link costs $10 per foot. The wood costs $20 per foot. So we have to use that information along with my beautiful picture of wood and chain link to write down the constraint equation, right? So now again, I have to probably copy this so you can kind of see it. Okay, so the chain link, I'll write as $10 per foot. $10 per foot. And the wood, right, we said was $20 per foot. Not foot per foot, dollars per foot. Okay. And we have a budget of $600. So that means, okay, so what's the cost of making this fence then as it is so drawn in this diagram? Okay, so the total chain link is 2y plus x, right? So the chain link, this side, this side, this side, that's 2y plus x. And so the cost of the chain link, of total chain link, right, link, is 2y plus x times 10, right? Because this is the total chain link is this 2y plus x feet. Chain link is $10 per foot. So the total chain link cost is 2y plus x times 10. So I'll kind of clean this up a bit. Now the wood is easy. So the wood is just one side. So it's this x is the wood. And it's $20 per feet. So the total cost of the wood is 20 times x. Okay, so then the total cost of building the fence is cost of wood, right, plus the cost of the chain link. And that comes out to just adding this equation with this equation. So it's 20x plus 2 times y, plus 2 times y plus x times 10. And that has got to equal 600. So that's the constraint equation. right? The total cost has to be 600. That's our budget. Okay, so we should simplify this a bit. So we have 20x plus 20y plus 10x equals 600. So in the end, we're getting 30x plus 20y equals 600. Okay. And now we can solve for x or y. It doesn't matter what we want to do here because they just want the maximum area. They don't want us to to say which one of the lengths are, so we're okay. So let's solve for x, I guess. So we get x equals 600 minus 20y divided by 30. So we get x equals 20 minus 2/3 y. And we, like we did in the previous questions last video, and we substitute this value for x back into the equation in step 2. To obtain that the area equals x times y is then 20 minus 2/3 y times y is 20y minus 2/3 y squared. Let me clean it up a tad. And so now this is a function of y. So I should just say, so area is a function of y. And now step 4 is we maximize this function using calculus like we did in the last several questions in the previous video. So maximize using calculus. Okay, so a of y is 20y minus 2/3 y squared. A prime of y equals 20 minus 4/3 y. And we have to set this equal to 0 and solve. So we get 0 equals 20 minus 4/3 y. And to solve this, I can multiply everything through by 3, and I get 0 equals 60 minus 4y. And so we get 60 equals 4y. And so we get y equals 60 over 4. Now, 4 doesn't divide 60, but we can simplify this a little bit. So this is, actually, no, sorry, it does divide 60. Sorry, it's 15. Duh. Okay, so it's 30 over 2, which is 15. Okay, so it's 15 feet. And now we need to use a derivative test to check if this is the maximum. Hopefully you're getting a sense for this now. So again, the second derivative test is very, very easy here. Oops, highlight. So this function, 20y minus 2/3 y squared, is actually a parabola that opens down. So this will be a maximum, but we can check, we can again apply the second derivative test. So applying the second derivative test, we see a double prime at y is minus 4/3, which is negative. So y equals 15 feet yields a maximum. And the max area. Now we need to solve for the area. So we have to plug y back into here to find the area. And you can use a calculator to do this. But so the max area is A at 15. Where's the area equation? Should copy this down. So it's over here. A at 15 is 20 times 15 minus 2/3 times 15 squared. And if you work this out on a calculator, you should get 150 square feet. So that's the maximum area we can build with our budget, enclose with our budget. So 150 square feet is the maximum area we can enclose with our budget of 600 big ones. All right, so that's a little bit, and it's not that dissimilar from the house question in that we're dealing with like a rectangular plot and we want to maximize the area, but the constraint doesn't involve a perimeter kind of constraint in terms of the amount of fencing, but extraneous information in terms of cost of materials. But this is a very natural consideration. You want to construct something, you have a limited budget or limited resources. How do you optimize what you can construct? And this is exactly how you would do it. But it required us making a little bit, where did it go? More elaborate of a diagram involving wood and chain beyond the geometry. So imposing other things on the geometry. Okay, so the next one is a variation on this problem where we're just going to reverse the roles of what we do. So we'll deal with slightly different equations. So this is our fourth optimization problem. So example 4. Okay, so same setup as before. But now we need an area of 216 square feet, but we don't have a budget. So we don't have a fixed budget. However, it would be kind of wasteful of us not to try to minimize costs, right? However, we still want to minimize costs. So the question is, how many total feet of wood and chain link fencing do you buy? Okay, so in this example, what we're doing is kind of reversing the role of the constraint from last time. So this time the constraint is the area, and the thing we want to optimize or minimize in this case is the cost. So last time the area was the thing you wanted to optimize, and the constraint was the cost. So we're reversing them here. So it would require a little bit of a different setup. We'll get to different equations. Okay, so it's the same setup as before. So, I mean, I guess I could just copy the same diagram, but where the heck did it go? There's the information we need. Right, and so that's our step 1 is kind of already done from last time. Now, step 2 is the cost. Now, we actually went through this in the last problem, right? The cost of building the fence we computed not the lost, the cost of building the fence we computed last time to be, right, the amount of chain link is 2y plus x times $10. Oh, sorry, plus the cost of the wood side, which is that. So that's the cost of the fence, I'll call C. Right, so we computed that. That was our constraint equation last time. Now it's the equation we want to optimize. That's what I was saying. Now, step 3, the constraint is the area, right? Is that the area, which is x times y, is $216 in total. Oh, sorry, feet. Sorry, area, feet squared. It's Monday. Okay, so now you can solve for x or y. I would probably solve for y because it only appears once in the equation for the cost, where the x appears twice. So you only have to replace the y once. So solving for y, we get that x is equal to, oh, sorry, y is equal to 216 over x. And we then substitute this into the equation for the cost. Let's see, so we substitute in the equation the cost to get 2 times 216x plus x times 10. So just putting in for y here, plus 20x equals the cost as a function of x. So now we need to do some simplification before we do any calculus. So if we simplify this, what do I get? So we get 432 over x plus x times 10 plus 20x equals the cost function. And I guess I should probably write it the other way now. So the cost function of x, you get 43200 over x plus 30x, and that's what we got. That's our cost function, right? So I'm just taking the 10, distributing it in here, and then you have 10x plus 20x is 30x. Okay, so that's step 3 all done. Step 4 is minimize this cost using calculus. And now the derivative here is a little trickier, right? So it's not, this is not a polynomial. We can still use the power rule, but this is not a polynomial function. This is a rational function. So we have a negative power. So I'm going to write c at x to be 4320 x to the minus 1 plus 30x. And so c prime of x is minus 4320 to the x minus 2 plus 30, right? And now, so that's just a power rule, but it's power rule with a negative power. So now set c prime at x equal to 0 and solve for x. So you get 0 equals minus 4320 x to the minus 2 plus 30. So you get 30 equals 4320 x to the minus 2. And now you can remember what is this x to the minus 2? So this is also the same thing as saying 4320 over x squared, right? So you can multiply both sides by x squared. You can just cross multiply. So you get 30x squared equals 4,320. And so x squared equals 4,320 divided by 30. And now, so x equals the square root of 4,320 over 30. And this is something, it would be plus or minus the square root, but this is a length, an actual length. So it's not going to be a negative length. So you don't take the negative square root. Okay, so I'm not skipping a step or omitting something. But now we need to use a calculator to kind of sort this puppy out. So this is x is then the square root of 432 divided by 3. What does that work out to be? All right, so when we work this out on our calculator, we get the square root of 144, which is 12 feet. And, we should check that this is a maximum. Oh, sorry, minimum. Sorry, minimizing cost. So we need to check x equals 12 feet yields a minimum. So where's our cost function? It's way back up here, right? So here's our data. And again, we can use the second derivative test. If you're comfortable with the power rule, we can again use the second derivative test and see what the concavity is at this point, right? So we may again, or we can again, apply the second derivative test. And check the concavity. Okay, but I need to copy the first derivative. There it is. So the second derivative is, now it doesn't matter what the sign is. Sorry, it doesn't matter what the actual value is. I'm not going to worry too much about that. But it matters what the sign of it is. Remember, it just matters whether the graph is concave up or concave down, bending up or bending down at the point in question that we're checking for a max or a min. So the second derivative is minus 4,320 times minus 2, x to the minus 3. And so this second derivative, again, turns out to be 8,640. That number doesn't really matter, over x cubed. And again, whatever this number is, it's clearly positive. If you plug in 12, it's clearly a positive number, okay? So by the second derivative test, the graph is bending up at the point where the tangent is flat. It's a minimum, which is what we want. Bending up at the minimum. Sorry, at the point x equals 12. So x equals 12 gives the minimum. Now we need to solve for y, because the question actually asked us, if you remember, the question asked us to provide both the amount of wood fencing and the amount of chain link fencing, right? So we need to go back to our little picture here. Fortunately, there it is. So X was the amount of wood fencing, actually. And now we need to find the amount of chain link fencing. So let's just remember the situation. Now, okay, so the area was 216, which was x times y. So if x is equal to 12, y is equal to 216 divided by 12, which on your calculator you can work out to be 48. And from the picture, from the setup in the picture, right, x is wood, y is chain link. So to minimize the cost, oh, sorry, it's not that, sorry. It's not that, x is wood and, sorry, this isn't right. Let me fix this. So the x is wood, chain link is 2y plus x. And actually 216 over 12 is not 48, sorry. So 216 over 12 works out to be 18. Thank you. Okay, so it's 18. And so we need 12 feet of wood. And we need 2 times 18 plus 12 equals 36 plus 12 equals 48. That's where the 48 is. I had remembered. Total feet of chain length. Okay, so the last step was a little more complicated than I originally remembered. You need to find, so once you have the, the minimum is when this length of the rectangle is 12, you've got to go back, figure out what the width of the rectangle is, y, and then translate that from this beautiful picture of wood and chains into the amount of chain and the amount of wood you need. All right, so sorry about that little mix up there, but I think we're good now. So we need 12 feet of wood and 48 feet of chain. Okay. So the last problem for this section involves a three-dimensional problem. It's very similar to this one, but it's a little bit maybe more involved because you have to think in 3 dimensions, but we can handle it. So last example. So an open rectangular box is to be built with a square base. And I'll actually, now this one is nice enough that they actually give you the picture. So, and I'll try to reproduce it here. Okay, so that's not bad for me. So the base is square. So the sides of the base will be x, okay, the length of the base here. And then the box has some height h, but it's open. Okay, so here, I brought a prop. Here's an open box with a square base. It was used to receive a Christmas present. You can see it's kind of Christmassy. And I kept it around because the cats were playing it for a while, and then they eventually lost interest. Okay, but anyways, it's a good prop for this question, this video. Okay, so there it is. So what we want to do is find the values of x and h for which the volume of the box is 32 feet cubic feet, okay, which is not, my Christmas box, not 32 cubic feet. And and the surface area of the box is minimized. Okay, so this is a situation where you want to minimize the surface area of the box, and when the constraint is a given volume. The box has a given volume, but you want to minimize the surface area. And this is, again, makes something you'd want to do, makes sense that this is something you want to do in practice, right? You want to build a box with a certain size, you can put something in it, but the surface area has to do with the material that you need to make the box, right? And so you want to keep that minimized because that's where your cost is going to be. All right, so it's kind of quite similar to the last one. The equations will be a little more complicated, maybe just a tad more, but it's not too bad. So we kind of have done step one here, drawing a diagram. The variables are laid out for us in this question. It's actually given to us. And so step two is we need to write down an equation for the surface area in terms of x and h. Okay, so I'll kind of use this box as a prop. Now I'm gonna fold in the sides, so just pretend the box is open. Okay, so you don't see those sides that we're flapping over with a nice wrapping paper on them. So the surface area is you have, first of all, you have the area of the base, of the square base, right? So I'll call surface area SA, and just in geometric terms, it's area of square base, right? And then you have the area of the four sides. So 1, 2, 3, and 4. Plus area of the four sides. Okay, so let's go back up to my lovely picture here. And we can try to put this in terms of mathematics. So the area of the square base, well, in blue here, that's the area of the square. So that's just like x squared. Now, each of the sides is a rectangle, right, with base x and height h. So, and there's 4 of them. So it's 4 x times h. Right, so, right in gray maybe. Each side is a rectangle of height h and base x. So the area of each side is x times h. There are 4 sides, so you have 4xh. So the surface area is x squared plus 4h. That's step 2 done. Step 3, write down constraint equation. And use it to simplify the equation for the surface area, like we've been doing all along. Okay, so now what was the constraint? The constraint was the volume, right? The volume of the box had to be 32 cubic feet. So the constraint is volume, I'll call V, is 32 cubic feet. Now we need to have an equation for the volume of the box. And so hopefully you remember some basic geometry, but the volume of the box is going to be the area of the base times the height, right? So it's a volume of a rectangular prism. It's the area of the base times the height. So volume equals V is area of base height. And so this is, in our case, where's our handy dandy box? There it is. So the area of the base is x squared, the height is h, so it's x squared h. Okay, and this is supposed to be equal to 32. So the constraint, just write it again here, is 32 equals x squared times h. That's our constraint equation. Okay, so now let's do surface area. Now I would really, now you have again choices in terms of how you replace the variables in the surface area equation, right? You could replace the x in terms of h, or you could replace the h in terms of x. I highly, highly recommend in this case replacing the h in terms of x, because if you go the other way, you'll have to take a square root, and that will make things much, much more complicated, right? Because you notice the constraint involves x squared, right? And this equation involves an x squared and an x. So if you try to like solve for x in terms of h, that's going to involve a square root. Then you'll have a square root in your surface area equation, and differentiating square roots or rational powers are much more difficult. So what I'm going to do here is for ease of algebra, we will replace h in terms of x squared. So using the constraint equation, we obtain h is 32 over x squared. And so we can substitute this into the equation for the surface area to get the following. Surface area equals x squared plus 4x times 32 over x squared. So I kind of clean this up a bit. As you get the surface area is x squared plus 128 over x, and there we are. Now this is a function of x, so I should write it that way. So surface area as a function of x. And now we're on to step 4. So use calculus to minimize this function. So we get surface area. The derivative is x squared minus 128 over x squared. Sorry, 2x. 2x minus 128 over x squared. Again, this is, if you want to write this in terms of powers, this is x squared plus 128 x to the minus 1. And I was so focused on the 128 over x that I forgot to differentiate the x squared. All right, so derivative is derivative x squared, which is 2x, and the derivative of this guy, which is minus 128 to the x minus 2, which I've written like this. Okay, and now set s prime at ax equal to 0 and solve. So you get 0 equals 2x minus 128 over x squared. I can multiply through by x squared, and I get 0 equals 2x cubed minus 128. So 0 equals, put this way, 2x cubed equals 128. So x cubed equals 64. So x equals the cubic root of 64. And you can use this on a calculator if you want, but 64 is 8 squared, which is 2 cubed. So this is 2 to the 6. Sorry, cubic root. So this is 2 squared, or 4. So x equals 4 is the point where the derivative is 0. And now we need to check this as a minimum. So we can again use the second derivative test. To check that x equals 4 gives a minimum and we just need to get the first derivative. There it is. Gonna erase these lines. So a double prime at x is 2, and now this is minus plus 256 over x cubed, and so this is always positive if x is positive. So 4 is positive. So x equals 4 is minimum. So we also wanted the value of h, right? So it also wanted us to tell us the value of the height of the box h when there's a minimum. To get the value of h, go back and substitute x equals 4 into the constraint equation. And when you do that, where's the constraint equation? There it is. No, that's not it. There it is. Right, so get rid of the box. So if you put in x equals 4, you get 32 equals 16h, so h equals 2. So the dimensions of x equals 4 feet and h equals 2 feet, so the height of the box being 2 feet, the base being 4 feet, yields a box with volume 32 feet cubed and minimal surface area. Okay, so that's the end of that. So I find these problems fun, but they're kind of tricky. There's several steps involved. And basically, I think the hardest part, as you've seen, is kind of setting up the problem, translating from the English into math, using some geometry and some pictures sometimes, or information about materials and cost, and imposing that on the geometry. And then finding a constraint, using a constraint to write the quantity to be minimized or maximized in terms of one variable, and then doing some calculus. The calculus is usually fairly easy. It gets a little trickier when you have these negative powers, but you just need to remember the power rule, right? So you might have been wondering, I skipped a step here, right? So here, what I did, if you're wondering, this is 128 x to the minus 2, and if you differentiate this guy, you get, so this is minus 128 x to the minus 2, you get minus 128 times minus 2 x to the minus 3, which is 256 x to the minus 3. Okay, so that's what I did, guys. That's what I did here. But so sometimes there's a little bit more difficult algebra or differentiation involved in some of these problems um, that than the others, but it's nothing too crazy. In the end, you're using the power rule to do some differentiation most of the time, and occasionally you have negative powers. But the second derivative test here, you see, was very, very easy. If you didn't like to do this differentiation, you could use the first derivative test here and check the sign. That's a bit tedious because plugging in x equals 4 and plugging in something like x equals 3 into this guy here, trying to figure out the sign, and then playing like x equals 5, the numbers aren't great. It might take you more time, but it just depends on how comfortable you are with going this extra step. So, all right. I hope you enjoy these problems. I think they're a lot of fun, but they're challenging. Practice, practice, practice. Go through these steps. Be systematic. Each step itself isn't too bad, but like I always say, putting together the steps that can be challenging. I'll be happy to help you guys in the live meetings.